Today we're going to start our topic on chemical bonding. First thing we want to address is, why do atoms bond? Well, the reason is to become more stable. It's the reason why certain atoms gain or lose electrons. It's also the reason why they bond. And if two atoms cannot become more stable while bonded together, they won't bond. We also have to learn a few of our notations. Chemists are notoriously lazy, and this here is no exception. So we have to learn about electron dot notation. Since those valence electrons are the ones that determine how an element acts or reacts, those are the important electrons to look at in an atom. And the way we do electron dot notation is it uses dots to represent those valence electrons only. So if this is electron dot notation for hydrogen, find the symbol for hydrogen, which is H, and then we have to decide how many valence electrons it has. It's in group 1, so we know from the last chapter that it has one valence electron, and so we put one dot beside it. If we were talking about bromine, then that is a halogen, and it's in group 17, and again from the last chapter we know that they have 7 valence electrons. And so those electrons are going to appear. I generally tend to go clockwise. The electrons do exist in pairs. So 1, 2, 3, 4, 5, 6, and 7. So it tends to be in kind of a little square around that particular element. So that's electron dot notation, tells us about those valence electrons. The other thing that we have to remember from last chapter is that the octet rule, that atoms want to either gain, lose, or share electrons in order to obtain a full set of valence electrons, or that magic number of 8. Now, everybody wants 8 except for the little guys: hydrogen, helium, lithium, and beryllium. So numbers 1, 2, 3, and 4 on the periodic table will often be happy with 2 because they just have that first energy level, and that first energy level can only hold 2 electrons anyway, and when it's full, it makes the atom happy and stable. But otherwise, everybody wants 8. And when they become ions, they're going to do whatever makes it easier to get to 8, whether it's gaining electrons or losing electrons. Whatever's easier is what they're going to do. So if we look at calcium, just over here, calcium is in group 2, and so it has 2 valence electrons. You can also see that by its electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So it has those 2 valence electrons, and so in order to get to 8, it can either lose those 2, and you can see here, then it would have 8 electrons in its outer energy level, or it could try and gain 6. But since it's going to do whatever is easier, it's going to lose those 2. And in fact, this becomes the electron configuration for the most popular ion of calcium, which is losing those 2 electrons, making it 2 positive, or a nice little cation there. We can also look at oxygen. Oxygen is in group 16, so it has 6 valence electrons. And so it's going to do what's easier when it becomes an ion to try and get to 8, so it can either lose 6 or gain 2. Well, gaining 2 is going to be easier, and we can look at it with electron configuration. It would look like this, and then it's going to gain 2 more, so instead of a 4 there, you'll have a 6. That gives it 8 electrons in its outer energy level, and so oxygen likes to become oxygen 2 negative. So you'll have some of that in the Bonding Homework 1 worksheet to do in figuring out whether an atom's going to gain or lose electrons. Just remember, they're going to do what's easier, and they're going to try and get to 8. All right. Let's see. All right. Now, what is a chemical bond? A chemical bond is a mutual electrical attraction between the nuclei and valence electrons of different atoms that holds the atoms together. Now, since this chapter is on bonding, I am going to expect you to know the definition of a chemical bond, but you can't memorize this one. It has too many words. So really, a good working definition for a chemical bond is that it is a force that holds atoms together. Whether that be an attraction between positive and negative, or whether they end up sharing electrons. That is a force that holds atoms together that makes them more stable. All right. So let's talk about the types of chemical bonds. I expect that you probably had some of these different types of chemical bonds in other science classes, or at least briefly talked about them. And that's all we're going to do here today in this lesson. It's just briefly talk about them, and then and we'll go more in depth later on next week. So, types of chemical bonding. The first type is ionic. You should recognize the word ion there, and that's really what's happening in ionic bonding. You have an electrical attraction between large numbers of cations and anions. It involves the gaining or losing of electrons. My classic example is NaCl, which is sodium chloride or table salt. That's what you have on your table at home. It is a very good example of ionic bonding. What happens is you've got sodium. It's in group 1, so it has one little valence electron. That valence electron is loosely held there by sodium. It has pretty low ionization energy. And it comes around to chlorine, which has 7 valence electrons. Well, chlorine, we know from our trends in last week that chlorine has a high attraction for electrons, high electronegativity. And so what happens when these two atoms get around each other is that chlorine pulls on the electron that sodium has and actually ends up plucking that electron off. And so what we end up is sodium losing an electron, developing that positive charge, chlorine gaining an electron, now it has 8. Sodium's also happy because it has 8 underneath, and it develops that negative charge, and it is the attraction between that positive and that negative that holds sodium chloride together. Now, it's not just one sodium and one chlorine. It is large numbers of cations and anions. So it's sodium attracted to multiple chlorines and chlorine attracted to multiple sodiums. And that kind of distinguishes it from the other types of bonding as well. All right, our next type of bonding is cooperative covalent. Covalent bonding results from the sharing of electron pairs between two atoms. So if they don't have enough strength to pull an electron off, they'll end up sharing those electrons. Now, if you have siblings, you know there are different ways of sharing. There's a sharing that happens and when your parents are around and you spend equal amounts of time with the particular toy. And then there's the sharing that goes on when your parents are not looking, and it usually involves the taller one holding the toy away from the younger one, and it spends more time with one sibling than the other. The same thing happens with electrons. Electrons can be shared equally or unequally. If it is unequally shared, we call it polar covalent. You have an uneven distribution of charge, and the bonding electrons are shared unequally. Your classic example is water. I need for you to go ahead and associate water is polar, polar, water. And later on when I ask and start talking about polar things, you'll say like water, and I'll say yes, because water is polar. So what happens with water, we've got 2 hydrogens bonded to an oxygen. So I'm going to do some drawings here. You're going to be able to draw these here in about a week. So now it's just about exposure. So I've got oxygen. It's in group 16, so it has 6 valence electrons. Then we have 2 hydrogens. Each hydrogen has 1 valence electron. And they end up sharing these electrons right here. Each hydrogen has access to 2, and each oxygen has access to 8. 1, 2, 3, 4, 5, 6, 7, 8. And that makes it a nice, happy, stable molecule. If you look at where oxygen's located on the periodic table, it's right there beside fluorine. Fluorine is the most electronegative element. Well, oxygen's pretty electronegative itself, and so it pulls on the electrons from hydrogen, but it's not enough to actually pull the electron off. So they end up sharing, but they're going to share unequally. And the electrons spend more time with oxygen than they do with hydrogen. Because it has more electrons spending time with it, it develops a slight negative charge. Here's the symbol for slight. It's a weird one, so slight negative. And because the electrons are being pulled away from hydrogen, it develops a slight positive charge on each end there. We call this polar because now the water molecule has two ends, oppositely charged. It has a slight negative end and it has a slight positive end. Just like the poles of a magnet, a north pole and a south pole. That's what we have here, and that's why we call it polar. We also have, so that's where the electrons are shared unequally. If they're shared equally, it is called nonpolar covalent. You have an even distribution of charge, and the bonding electrons are shared equally. Our classic example is chlorine gas. This is also known as mustard gas from World War I. What happens with chlorine gas is I've got one chlorine, which has 7 valence electrons, and another chlorine bonded to another chlorine that has 7 valence electrons. We end up sharing these, and each of them end up with access to 8. Well, this chlorine is pulling on the electrons this way, and this chlorine's pulling on the electrons this way. But they are pulling with the exact same force because they are the exact same element. And so no one wins this tug of war, so they end up sharing those electrons equally. So usually nonpolar covalent bonds exist when two identical atoms are bonded together. All right, so we have ionic, which is gaining or losing electron, and it's that positive attracted to that negative. Then we have covalent, where they're going to share. They can share unequally, and that's polar, where they have the opposite charges. Or they could share equally, and that is called nonpolar, and there are no charges in nonpolar. The last one is called metallic bonding, and it results from the attraction between metal atoms and the surrounding sea of electrons. That is a strange phrase, but it is one of the key phrases for metallic bonding. And it's not one that I made up. What happens with metallic bonding is kind of like a potluck dinner. Everybody brings a dish to a potluck dinner, and then when it comes time to eat, you can eat from or take some from every single dish that was brought to the table. Same thing happens with metallic bonding. Each metal donates its valence electrons, and then the atoms aren't attached to each other. They're just attached to this mass or sea of electrons. And so our example here, copper metal, it's made up of a whole bunch of copper atoms bonded together, and so we just represent it with the same symbol from copper.